Good evening. For the assessment given by the SSD module, we were asked to identify vulnerabilities in a given application and fix them. We decided to go with the one of the applications we decided in the microservices architecture in our third year assessment. So in this application, we were able to identify 11 vulnerabilities, and out of 11, I was able to do 3 and fix them. The first one was weak password hashing. So the issue was when a user forgets their password and they want to reset it, our system did not support that at all. So it was completely broken. We were using a security method called bcrypt to scramble the reset codes before saving them. But bcrypt created a different scrambled version every single time, even for the same code. So when a user entered their reset code, we could match it because we were comparing it with a completely different scrambled version. So that meant nobody could actually reset their password using our system. We fixed it by changing to a different method called SHA-256, which always creates the same scrambled result for the same input. Now, when the user enters their reset code, we can properly match it and let them reset their password. I'll move to my second vulnerability, which is X content type. The problem was that our application was not telling web browsers how to handle files safely. There's something called MIME type sniffing, where browsers try to guess what type of file they are looking at. So this is dangerous because a malicious file could trick the browser into thinking it's harmless image when it's actually a dangerous script that could steal user data or take control of their session. So the solution was I fixed this by adding a security feature called helmet middleware. This automatically adds a special instruction to every page we send out, telling browsers don't try to guess what this file is, just use what we tell you it is. So this prevents attackers from uploading malicious files that could harm the application. So that is the second fix. I'll move to my third vulnerability, which is invalid login attempt handling failure. So in my third vulnerability, the problem was that our logging system had no protection against attackers. Anyone could try to guess our password as many times as they wanted. There was no limit, no blocking, and we were not keeping any track of suspicious activities. So hackers could run automated programs to try thousands of password combination without any consequences. So the solution was we implemented 3 layers of protection. So we added a rate limit. So this is showing you that the invalid attempts, how it works. So it says password is incorrect second time, third time, and here it gets locked for 15 minutes, and it says your account is temporarily locked. So if someone fails to log into the same account 5 times, we lock that account temporarily to protect it. So that is my third vulnerability and the solution. Thank you.
Good evening. I'm Minupudara. In our project, I focused on the strengthening authentication and data security. First, I improved the refresh token mechanism. Previously, the system only used long-lived access tokens, which increase the risk if stolen. I implement short-lived access token with secure refresh token that can be rotated and revoked. This not only reduced the attack window but also gave the user the smoother login experience without frequent re-authentication. Second, I addressed the sensitive data exposure. Our application was leaking sensitive details through logs, hard-coded values, and debug messages. To fix this, I moved all sensitive values to environment variables, removed unnecessary console logs, and disabled debug info in production. This ensured the proper data privacy and protection against information disclosure. Then I implement the Google login using OAuth. This is the function. Then I can see the profile. This is the Google login. Thank you.
Good evening. I'm Asidhu Kallahara. I will explain two common web vulnerabilities: cross-domain misconfiguration and NoSQL injection, and how I detect and fix them using OSAP, SAP, and SonarQube. First, I will explain cross-domain misconfiguration. This happens when your server allows to request from any domain, often using asterisk in cross. That means any website can call your API, exposing data or enabling attacks. I found this using OSAP SAP, which flag open close issue during a scan. To fix it, I applied the strict course policies. Only whitelist domain are allowed. HTTP methods are limited and credentials are handled by safely. This ensure only trusted client and access the API. And second, I will explain no SQL injection. No SQL injection occurs when user input used directly in database queries like MongoDBs. Attackers can send the uh, payload to manipulate queries and steal data. SonarQube detect in my project warning about queries built from rig.body.ids. To fix it, I add the input validation. Each ID is checked with mongoose.types.object ID is valid before being used. Invalid input discarded, prevent injection. In short, use strict course policies to prevent the course domain attacks and validate all use input to block NoSQL injection. These steps make web apps much safer. Thank you.
Hello, I'm Sachit Prasada. I will present the vulnerabilities I define and fix. Uh, First one is course misconfiguration. Uh, Originally, our backend allow requests from any domain. This means any malicious websites could interact with our APIs. Uh, uh, I changed this restricted course policy, allow only our trusted front-end domains. This ensure only legitimate clients can send requests. Second one is NPM dependency vulnerabilities. Uh, our project contain outdated NPM packages with non-security roles. Uh, this introduct high risk vulnerability to both direct and transitive dependencies. I run NPM audit updated packages, yes, secure versions and tested compatibility. Now we have updated and stable dependencies without non-series. Next one is server leak. Uh, the application expose its technology stack via XPathway header, revealing Express framework detail to attackers. I used to helmet middleware to remove this header. Now, 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 no unnecessary server details are leaked, uh, reducing risk targeted attacks. Last one is Stripe client ID and webhook. Uh, Stripe client secret was stored in our database, which could be leaked and misused for payments. Also, we updated payment status without verifying Stripe authority. Means attackers could fake completed payments. Uh, I remove client secret storage, keeping only payment intent ID. The secret is sent once to the front end, uh, never persisted. Uh, and I added secure Stripe webhook using signature verification with Stripe webhook
construct event. Now only genuine stripe events can update payment status. Uh, these fixes transformed insecure practices into secure implementation, reducing risk exposure while aligning with OSAP top 10 categories. Thank you.